have been talking about synthesizing flow diagrams and flow diagrams with multiple process units. Okay, so we've got a process to make adipic acid from which is 4-nylon. We're going to use E. coli to take glucose. It's going to need oxygen metabolize. It's going to make gluconic acid, and gluconic acid, that's going to happen by the E. coli. We'll use the bacteria to do that for us. Then we're going to later take the gluconic acid, hydrogenate it, and get adipic acid. That's the problem. I think we drew out the whole flow sheet, yes? Okay. So let's see. Glucose, which is going to have to come in solution with water. Let's make a mixer. We need air and we go to a reactor where we're going to get out the gluconic acid. And we said we need a separator. And we're going to take out nitrogen and CO2, and we're going to take out water, E. coli. That's going to give us gluconic acid. Go to a second mixer where we need to get hydrogen. Second reactor where we get adipic acid. Okay, and then this is the problem we want to play around with. So determine all component flow rates for your process for the production of adipic acid from glucose. Design your process. So we're pretending this is a brand new process, a different way of doing it. We just want to throw some things down and start getting some estimates. So we make up a process, and then we start taking our best guesses of what to do. Anish?
I remember last time, whenever any of the reactants went through a reactor, you would show that they were still left over after the reactor. So do we have to do that every time if it doesn't tell us that it doesn't?
Yeah. Do we have to? Not necessarily. So if this is a design exercise, we don't know what this is like. The general case, yeah, reaction doesn't go 100%. So you keep all the reactants in the product. The new problem statement I've given you, I don't know if we read this one, says design your process to use glucose, blah, 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 blah. You may assume 100% conversion. And this is given in the problem statement, but if you're doing this for scratch, if you're working for Genentech and trying to see if you can come up with bacteria to do this, you could say, let's make it simple to start. Let's assume 100%. And later you can redo the calculation. If 100% isn't going to be profitable, you might stop right there, right? So it's a good place to start. Yeah, that's a good question. So okay, design your process. Glucose in solution at 10 mg per mil and oxygen from air, which we talked about before. So if we have 100% conversion, let's see, and we produce 1,200 kilograms per hour of adipic acid, 12,000 kilograms per hour. You may assume steady state and 100% conversion in both reactions. Okay, so now does it make sense? Let's see. So yeah, okay, so Murphy's 10 steps. Step 1, draw a diagram. Choose a system. Step 2, label your variables. So here's the start of the diagram. Part of step 1 is choose a system. What's a good system to choose for this? Multiple process units. So we have 10 steps. Murphy's 10 steps with multiple units. Step 2, choose a system. This step is a little different than what we've done before, so I'm going to write out some of the system steps that changed. So what are our choices for the system? 1, 2, 3, 4, 5. So I got 5 boxes here. I could choose any one of those. I could choose reactor 1 as the system. I could choose mixer 1 as the system. mixture 2, reactor, I could choose any one of those 5. I can also do combinations. I can take mixture 1 and reactor 1 and put them together. Any of these choices are fine. All of these are valid. They might not all be the easy way to solve the problem. What can you tell from intuition what's the best way to go after this problem? Troy?
All five process units of the system.
All 5 process units. Why?
Because you already know what's going to go in and what's coming out.
Yeah, so I know stuff about what's going in. I know stuff what's going out. If I lump all this together, I don't need to worry about all the details in between. So often my choices are each unit in the in turn. We could just do one at a time, or we could do the whole system. Which is really equivalent to, if we draw one box and just show all the inputs and all the outputs, what do we call that? That's an input-output diagram, which we've done before, and they're usually easier to do. Or we can do combinations. We do each unit in turn. This could either be, often you want to start from the start or from product. Sometimes it's easier to start from the product and work backwards. So you got all kinds of choices. Okay, so let's do this one big box. If we do that, this diagram becomes much simpler. We've got air with oxygen and nitrogen. We call this stream 1. We've got stream 2 with glucose and water. So I've got, just to keep the inputs together, my third input is hydrogen. Let's call that H3, call that stream 3. And I've got outputs here, here, and here. So let's call the top one stream 4, and we'll put nitrogen and CO2 in stream 4. Stream 5, out the bottom, we'll put water in stream 5. E. coli is a little tricky. We're going to skip E. coli. E. coli eats stuff, grows, multiplies. We're going to ignore the E. coli for a moment because it's a simple, just a simple design calculation start. Finally, stream 6. This will have the adipic acid. Process. Adipic acid. Okay, any questions about how to choose a system, draw the system, and then redraw your diagram so you have a simple drawing to work off of. So you can ignore this for a little while, and we can just work off of this diagram to try and solve our system. All right, once we do that, it looks like what we've done for the last 2 weeks. We've got one box, we've got inputs and outputs, we can write a bunch of equations. There's 2 reactions. There's also another little trick with this one. Because we've encompassed both of these together, because we never see gluconic acid, one thing we can do is write this as a net reaction where we add the 2 of them together, stoichiometrically. I don't know if I got that H2 right, because we had that typo we found last week. Anyway, so we can have a net reaction and ignore gluconic acid. 1,200 kilograms per hour. If I go with 146 kilograms per kilogram mole, this becomes 82.2 kilogram moles per hour of adipic acid. The other one, 10 milligrams of glucose per mil of solution. I've got to get the density of the solution to go from volume to mass, and then I've got to get mass of glucose and mass of water. You can figure out that I'm going to have about 0.01 grams of glucose and 0.99 grams of water. If I add those together, I can get kilogram moles of each. So 0.00106 kilogram moles glucose per kilogram mole of water. You guys can do these kind of right? This was like week 2, we did a bunch of these conversions. So this will come, as you saw in the problems last week, this just comes as part of the problem. So they'll be embedded in the problems, probably also in the exam. Troy?
Is it 1,200? Is it 1,200 in the problem, or is it 12,000?
Yeah. 12,000.
Okay.
Yeah, base.
No problem.
Step 5 is the basis. What's the basis? 822 kilogram moles per hour AA is what variable? Is A6. Okay, so it's easy to see the basis. So there's a flow rate here, 12,000 kilograms per hour. That's the basis. And I want you to pick a variable. Step 1 or 2, had this diagram and you put all these variables out here. Use these variables, put it together with the variable. I don't care what you call this variable. If you want to make this a happy face, and happy face is 822 kilograms moles per hour, you can do that. It's your prerogative to find your variable. But I like A6 because it's really intuitive to me. It's stream 6. Actually, it's pretty standard in the chemical tree to number the streams, and then to do that. And then, yeah, I like using capital letters to go with it. But whatever variable you want is fine, but give me a variable that relates to your system in your drawing. Okay, let's see that. Step 6 is system variables. Now, Emily, what do you have for system variables? Give me one system variable.
Water in plus water generated equals water out.
Water in plus water generated equals water out. Which is the system variable?
Water gen.
W gen. Inside the system, water is generated. Comes out of the reaction. 11 H2Os are on the receiving side of the reaction. What other system variables do we have? What else is generated? C, generated or consumed?
C gen.
Okay, what else?
A gen.
A gen, we better generate some product. What else? We got water, CO2, adipic acid. What do I do about hydrogen on the other side?
H consumed.
H consumed. What else is consumed?
O consumed and G consumed.
And what's the first one?
G.
G, glucose consumed. How many system variables? 6. See, so if I do variables, remember my friend, I've got some stream variables, streams. O1, N1, G2, W2, H3, N4, C4, W5, and A6. 3, 4, 5, 6, 7, 8, 9. I've got 9 stream variables, system variables. How many system variables? This is a trick question. Sorry. How many think 6? Brendan, Alex, son. So I have sympathy for you because there's 6 variables there. C gen, H consumed, W gen, O consumed, A gen, G consumed. I mean, as a mathematician, I look at this and go, hey, there's 6 variables there. So let's just remember that. Who's got a different answer? Aggie?
It's page.
Paige.
1
1. Why do you say 1?
for the reaction, because as soon as you set one variables, all the other ones are determined.
As soon as we set one variable, all of these are determined. We know how much C is generated, all of the rest comes together. Anybody have another answer? Keel?
7,
7?
because I think we just talked the reaction as a winner.
The reaction and all of these? Anybody have another answer? Okay, I like 2, because there's 2 reactions there. It really bothers me that the answer's not 2. Okay, so Murphy, if you read the 10 steps, you read the degrees of freedom, it says count one per reaction. Just one per reaction. So Murphy would say, I don't know, I read that, I want to do two, but really you don't, the reason you don't have two is because these add together and they exactly link and they're both 100% and it acts like one equation. They're actually, because you lose the gluconic acid in the middle, it's one reaction and that relates all of these. Okay, so there's one reaction. If you were Brendan or Alex on and you wanted to use these 6 variables here, then you also need to write all these equations. Cgen is, let's see. Let's start again. Glucose consumed equals 7/3 H consumed. Where did I get that from? Every mole of hydrogen, except I'm scared now there should be 2 hydrogens.
That should be
That should be 2? 2 hydrogens should give me 7/3 moles of glucose. So 2 glucose equals 7/3 H consumed. So then I could go down the list and write all of these equations. 2G consumed equals 17 halves of oxygen consumed. 2G consumed equals adipic acid generated. Also equals 8 CO2 generated, also equals 11 water generated. If I do that, 1, 2, 3, 4, 5, that looks like 5 equations right there. 5 equations, 6 variables, that gives me 1 degree of freedom, and that's what Murphy told me to do, just count one reaction. Alex and Brendan, are you satisfied? Can you write all these equations, and write all these variables, and say, okay, yeah, net, I've got 1 degree of freedom. Okay. Well, for the rest of you that, besides Alex and Brendan, you actually do want all these equations. This is what's going to help you solve this. So write down all these equations. In fact, the step 6 that says write down system variables says to write down all these equations, to use the stoichiometry and write these down. Okay, so we'll use all those equations. And these have to go in moles, so this only works because we're using moles. If we're using mass, you have to do other things there. Okay, what else? Okay, we at least have all the variables up there. Let's do equations. How many flows are we given? You know, A6 is the basis, 822 kg moles per hour. So there's one. Any other flows? How about stream specs? Stream composition specifications. Do we have any of those? 2. So the first one, glucose and water. So this is G2 over W2. 10 mg per mil. That's not the right units. But we can convert this into kilogram moles per kilogram moles. And we have an equation that's right for those numbers. Yeah? Second stream spec. I don't see another one up there. We use the 10, we use the 100% conversion, 12,000. What's the other stream spec? It's kind of another trick question. Ollie? Air. What's the composition of this stream of air? Oxygen, nitrogen O1 to N1 is 21 to 79 moles per mole. Okay, so it looks like I've got, so far I've got 1 flow, 2 stream specs, and last 4 equations, running out of space, material balances. How many material balances? Well, I get 1 for every species. Oxygen, nitrogen, glucose, water, hydrogen, carbon, adipic acid. I missed a 1, 2, 3, 4, 5, 6, 7. I missed one. Nitrogen, it's an error, it's not in that reaction. Oh, I did, okay, sorry. Am I good then? 1, 2, 3, 4, 5, 6, 7. 7 material balances, 7, 8, 9, 10. So I have 10 equations. I have 10 unknowns. Okay, do you believe we could do this from here? I didn't write any material balances. Can you give me a material balance for oxygen? Material balance, in minus out, plus gen, minus consumption equals accumulation. Oxygen, how much goes in? O1, how much goes out? Nothing, how much generated? Nothing, how much consumed? O consumed, how much accumulated? 0. So oxygen in equals oxygen consumed. Really easy equation. Nitrogen. Nitrogen in, nothing consumed, nothing generated, it's going to equal nitrogen out, which comes in between 4. N1 equals N4. O1 equals O consumed. G, G2, got to equal G consumed, etc. You could have a list there. Any questions about this? How would I organize this? I would make a stream table. Stream 1, 2, 3, 4, 5, 6, and I would put numbers in. Oxygen, 699 moles, nitrogen, 2628 moles. Stream 2, stream 3, each of the 7 components, put all that together. It's a nice, convenient way to take a big problem with lots of streams. Do that. Once you solve that, we're partway done. That was the first system we chose. We got that. We actually then want to go back to this guy, and now we can do each one at a time. Now that we know O1 and O2, O1 and O2, and we know G2 and G2, we can do the mixer. And you can tell me what comes out of the mixer, what comes out, what went in. Then you can do the reactor, and you can tell me what comes out of the reactor. Then you can do this separator. If we do that, we can label all the streams in between, give them other stream numbers, and I can end up with a stream table with all of those intermediate streams and all other pieces going through. We can do a bigger unit, so I can label streams 7, 8, 9, the intermediates, and do that.
In the winter